Hello everyone, welcome to what will be pre-lecture number 33. I'm going to talk about heating and cooling curves in this pre-lecture. So, let's see, about a couple weeks ago in our thermochemistry chapter, we talked about this equation here where we can quantify the heat energy of something if we know its mass, its specific heat capacity is what I should say, C, and then its change in temperature. And of course we can measure these, or we can figure them out if we are given information about some of them. And so we're actually going to bring that equation back and talk about it with regards to phase changes now. So this equation works well when something's being heated and cooled, but once it starts to change phase, we need a new equation to describe the amount of heat that's being transferred. And so, just as a kind of real-world example, think about heating a pot of water to the point of boiling. We can certainly quantify the amount of heat energy that we are adding and putting into the liquid water using our Q equals mcat equation, because our mass of water is going to stay the same, specific heat of liquid water is the same. We can measure a change in temperature and figure out Q. But once we reach the boiling point, the temperature where our liquid starts to transition into a gas phase, we now need a new way to quantify that heat energy. And so we're going to use this equation here, this Q equals N delta HVAP. And I should have defined this on the slide, and I'm sorry I didn't, but N is going to be our number of moles, and then delta HVAP is what we discussed last week. That is our heat of vaporization, okay? And that is an equation we're going to use during a phase change. And something I want to point out here is we don't have any term for temperature in here. And that is because as we are undergoing a phase transition, our temperature is going to remain constant, okay? So if we were to chart this, our y-axis is going to be our temperature. Our x-axis is just going to be the amount of heat added. This is usually, of course, across time. So if we started with a sample of ice, let's say, that was at negative 10 degrees Celsius, our first thing to do would be, if we added heat, we'd start to warm the ice up until we reached its freezing point, right? That represents another phase transition where we are going from a solid to now a liquid. And you'll notice, as we undergo this phase transition, we are not changing the temperature, aka we don't have any change in our y value, but we can still quantify the heat that's added using our Q equals N delta H of fusion equation, okay? Once all our ice is melted, our temperature will start to raise again. We can use Q equals mcat to quantify that amount of heat that we add, and then if we raise the temperature enough to where the water starts boiling, we have a phase change again, our temperature levels off, and then if we kept heating our gas molecules, that would continue to raise in temperature once all of our liquid was turned into a gas, okay? So if we were to quantify this, a word problem that might do something like this is how much heat is added to raise the temperature of 35.9 grams of water from negative 45 degrees Celsius to 155 degrees Celsius. And I give you basically a bunch of constants here. So we have specific heats for the solid, liquid, and gas of water. We also have the enthalpy of fusion for water and the enthalpy of vaporization, or the heat of fusion and the heat of vaporization for water. So our first step would be to think about where on this curve are we starting, and in this case we're at negative 45 as our initial temperature. So before we can do any sort of phase transition, we need to basically warm our solid ice up to 0 degrees. And so that would be our first step. At that point, we have ice that we would begin to melt, so it's phase transition. Then once all our ice is melted, we have liquid water. We would heat that from 0 degrees Celsius to 100 degrees Celsius. And then we would begin to boil the water and then heat the steam, the gaseous water, from 100 degrees to 155 degrees Celsius, okay? And if we started doing the math there, again, if we're heating something, if we're changing temperature, we use Q equals mcat. Where we have the mass, we have our specific heat of the solid, so we want to make sure we're using the correct phase there, so that's that 2.09 joules per gram degree Celsius. We multiply that by the change in temperature, which is going from -45 to 0, right? And so if we calculated all that out, we get 3,380 joules, because grams and degrees Celsius cancel out as units. We're left with the amount of heat energy that we have. Our next step would be to melt the ice, and if we're undergoing a phase transition, we want to use our Q equals N delta H, in this case delta H fusion, because we are melting, we are going between a solid and a liquid. So if we start with a mass, something that you'll notice here is that the enthalpy of fusion values are given to you in kilojoules per mole, and so we need to take that mass that we start with, convert it into moles, so this is just the molecular weight of water, then multiply it by our enthalpy of fusion. When we do that, we get 11.9 kilojoules for the phase transition. Okay? We're going to do the rest of this problem in class. If you want to, you can of course work ahead and finish it on your own, but if not, we're going to take some time during class to finish up steps 3 through 5 and then figure out the total amount of heat energy transferred. Okay? That's it for our pre-lecture. Hope it was useful. If you do have any questions, please let me know. Otherwise, I will see you in class.